So welcome everyone to the fuzzing and formal verification spaces with runtime verification, ACI, and EF. I would like to introduce all three companies, and maybe we can start off with Joseph. Could you introduce yourself at ACI?
Yeah, so hi, thanks for the opportunity. So we are ACI Blockchain. We are the smart contract auditors. We are auditing mainly EVM, but our goal is not just to be the auditors, but we also want to contribute to the ecosystem. So we are developing some tooling, and this is the reason why we are so keen on fuzzing. And this is a topic that we will cover here. And our main tool that we are developing is called Wake. So we will hear more about Wake here, and thank everyone for being here. And I'm looking forward to hearing more about formal verification versus fuzzing.
Thanks, Joseph. Raul, can you introduce yourself and runtime verification, please?
Yeah, so thank you everybody for joining this space. My name is Raul Schafranek, and I'm with Runtime Verification for 3 years now. And Runtime Verification is a security company that focuses on formal verification for the blockchain space. But originally, we come from a different domain. So our CEO is actually an ex-NASA researcher, where he developed a new technique to do formal verification, which is called runtime verification. So that's where our company name comes from. And now we're bringing the same tech that we used, or that our CEO used at NASA to secure the blockchain space. And the very nice thing here is, that smart contracts are very isolated systems, usually very small code size. They are not very dynamic in the sense that they cannot read much IO. They don't have much IO operations during execution, so that makes them a very good target for formal verification.
Thank you. And last, we have Nick from the Ethereum Foundation. Nick, if you could introduce yourself and what the EF does.
Sure. So hi, I'm Nick, or Ganidin on the internet. I work on the Ethdebug project, which is part of the Solidity team at the Ethereum Foundation. As I'm sure everyone knows, the Ethereum Foundation's mission is to do what is best for Ethereum's long-term success. And so my work is, I guess, part of that. It's centered around improving debugging tools for EVM smart contracts. Some of you might remember me from my work on Truffle, where I architected and oversaw the Truffle debugger. And generally, I just spent the last 6 years of my life when I was working on Truffle doing data modeling related to the domain of smart contract development. I've been working on Ethdebug since October, November of last year. And my work specifically involves creating a data format that compilers will be able to output, and then debuggers could read that output. Similar to how Solidity itself has a compiler input format that's in JSON. The Ethdebug format will also be JSON, and the idea is that Solidity, Viper, etc. They could read the developers could read the Ethdebug format specification and then modify their compiler to provide this information for future debuggers to use in understanding the EVM and users code.
Thanks, Nick. Can you run us through the current state of debugging on Ethereum and what's possible out there?
Yeah, I'd be delighted to. So there's a few Solidity debuggers that exist today. I'm not sure about other languages off the top of my head. I think there might be some kind of solution for Viper. But of course, runtime verification is symbolic. But Remix has a debugger. Tenderly has a cloud-hosted debugging solution. Truffle had a debugger, while the project was still alive. But the reality is, and I'm mostly speaking from my experience with Truffle Debugger, although I bet this applies to all the debugging projects, and that is it's exorbitantly expensive to build and then continue to maintain a debugger for an EVM language. Now, I don't have exact figures, but the ballpark that Truffle and Consensus spent on Truffle Debugger was around $2 million, and that was about 4 or 5 years of work that went into that. 2 or 3 people at any given time. The reason that it's so expensive is because the EVM is complicated, and as a result, the high-level languages have to do complicated things. Like, it's a public blockchain; it has to concern itself with cryptographic primitives. There's these, 32-byte word sizes, contract state variables. They have to be organized into storage slots. It's just the reality of the EVM that you have to be clever if you want to allow users to use structs, arrays, strings, etc. And so, like, that complexity, when you're building a debugger, at least today, you have to write a bunch of, I want to write a debugger. How do I do that? Well, you have to write a lot of Solidity code, and then you run that Solidity code, and you have to observe the EVM in binary, right, or hexadecimal. And, well, you wrote a string, you have to see how the string behaves. You write an array, you have to see how the array behaves. And this is different for every data type, right? Like a fixed size array that, it always has 10 elements, behaves completely differently than a dynamically sized array, which could have any number of elements. And it's not just those, it's like every single data type has some behavior that if you want to write a debugger, you have to observe what the language does at the machine code level. And then let's say you get that right, you release the first version of your debugger, and the compiler that you're relying on, they change their behavior because they want to improve performance, they want to decrease gas costs, etc. And so you're constantly, beyond the initial upfront cost, you're constantly at risk of spending a lot of money redoing all of your work. And it's just, it's kind of untenable.
How does the current state of debuggers impact auditing and fuzzing in particular? Michal, if you could take this question.
Yeah, sure. So as Joseph said, we are developing a tool called Wake. Wake is like a lot of things, but in this context, we are talking mainly about testing. And in testing, of course, we need to debug. We need to debug transactions, but it's not only about debugging transactions. Basically, Wake is a Python-based tool, so we are writing tests in Python, and then we execute some transactions. And since we are testing in Python, we can use the Python debugger, which works very well, and we can do many things that we probably even couldn't in Solidity. So we can write in the debugger, we can deploy new contracts, we can send new transactions, and so on. So yeah, this is pretty good. And basically, you can observe the state before a transaction, the state after the transaction. But where we really struggle is when something breaks inside the transaction, when we just need the data from the transaction from the inside, not from the end or from the start of the transaction, but from inside. And this causes us a lot of troubles when debugging these scenarios, and also a lot of time. I got a few examples. The first one is ABI encoding and decoding. So sometimes these encodings and decodings in Solidity fail, and when they fail, they just revert, but with no data. So we don't know anything, like we know nothing. And yeah, it's really hard to debug things like this from Python. It's almost impossible. The second, sorry, Nick?
I was just laughing because I can relate.
All right. A second example is when there's a mismatch in a signature. So mainly when signing structured data, like the IP712, the problem here is that we cannot know the pre-image. So we need all the values from inside the code. So yeah, again, we would need to be inside the Solidity debugger. So we would see all the values, and this would make the signing or even the catcher hashes, debugging of these hashes and signatures easier. And this is something we cannot currently do, and we spend a lot of time on that. And another example is when we run out of gas and we don't know where we exactly ran out of gas, which is also quite an issue. So yeah, and what we can do currently is that we can print call traces, we can print console logs, or use console logs, use the log console, but it means that we need to recompile the Solidity code every time. We need to add more console logs. And in the case of call traces, we can only print the external calls. When it comes to internal calls, it does not work when the optimizer is enabled, because yeah, The optimizer can do many things, and I think this is maybe the case when debug format could help us in the case of internal calls.
All right, so debugging is critical infrastructure, and sometimes you have the case where you get some issues which you are impossible to debug. I have a question to Nick. Is there something that the EF is working on to like further improve this, or are you working on something specific at the moment at the EF?
Yes. So the EF is, and specifically the Solidity team, they're funding my work on the Fdebug format, and that's designed to eliminate, the experimental analysis that I was describing, right? Or what, having to inspect the inside of a transaction or an internal call. Like doing that requires you to understand how the language works, and so the Fdebug format is designed to sidestep that concern entirely, right? It's like, let's say the compiler tells you, here's where you find a string, or this array was just initialized, it's safe to look at it. If you have this information, produced by a compiler, then it saves the upfront work of figuring out how that compiler behaves, but it also saves you from all the follow-up work around, making sure your assumptions continue to hold, as the languages and tooling landscape change. So my work specifically is to figure out what these symbols, what the debug information should look like. This is like a solved problem for traditional computing platforms. Like, yeah, you can use the Python debugger quite well because it's an understood problem on traditional computing platforms. A huge body of like decades of work solving this problem. But it's a lot more complicated for the EVM. And as a result, it becomes very non-trivial to address this debugging concern that is critical. And, so as a result, there's like a number of constraints that we're dealing with. They're like kind of non-negotiable requirements versus other platforms, right? Like you have to be able to debug optimized code, for instance, if you want to understand $1 million contract hack on mainnet, right? That's not going to be running in your development version, your development build. That's production. So you have to be able to debug that, and that complicates things substantially. So, my work is initially going to just be to describe the information that is necessary, right? And then work with Solidity, work with hopefully Viper and other languages to actually support this format. And then, Aki, RV could, it is my hope that they'll read this format and not have to spend millions of dollars building and maintaining debuggers.
Yeah, it was pretty sad that Truffle went out of business. So let's hope that we can stop that from happening to other tooling. Raul, maybe you can talk about what tooling you guys are building at the RV, at runtime verification.
Yeah, so as I said, runtime verification focuses on formal verification. And interestingly, when we invented symbolic, it was not just, hey, let's build a cool debugger because Solidity doesn't have so many. But we actually came there from like different perspectives. So first of all, we also do audits at runtime verification. When you're doing an audit or a classical manual security review, then you're looking at Solidity code, and there's so many levels on which you need to understand the code. You need to understand like the high level business logic that's behind the financial incentives. You need to understand the Solidity semantics very well. Sometimes you need to look into disassembled or into assembly code. And while you're auditing, you usually don't want to waste too much time on the low level details. You don't want to spend like a lot of time reading and interpreting Solidity semantics and documentation. And so what we find ourselves doing is during audits, we were plotting or diagramming out smart contract system with pen and paper, like tracking state updates of smart contracts, of transaction traces manually. I literally filled like thousands of white sheets of paper with diagrams that I've drawn just to keep track of the Solidity variable. So I wasn't even getting on the I wasn't even getting the high-level picture. So we thought, well, we need a way to automate keeping track of all the low-level details. And then we experimented with different approaches of visualizing control flow, of visualizing state updates, and ultimately we converged against a debugger, which seems to be the ideal, or well, at least the best user interface that we have to debug source code languages. And then also, well, we do formal verification on the bytecode level, right? Because ultimately the Ethereum blockchain does not run Solidity code, but it runs EVM bytecode. So, and when we formally verify the bytecode, well, sometimes you get stuck at some point. So your prover, like formal verification is not an fully automated task. You don't press a button, and at the end it tells you, okay, here's a proof that your code cannot break, or it does not say, hey, here's a counterexample that I found. But in many cases, your prover will get stuck. And then, well, you need to investigate and see what's going on. How can you guide the prover to make more progress on your proof? But now you are kind of in a very unfortunate situation, because now you're looking at really low-level EVM data structures like memory, storage, the stack, the bytecode, and you don't know where in your Solidity source code you actually got stuck. So, and then we figured, well, we could maybe use the same user interface that a debugger offers to connect to our formal verification tools. And I think that's the most distinguished feature of Symbolic, is that it's not just a classical Solidity debugger, but it's also a symbolic execution debugger, which means, well, when you're doing formal verification, you are introducing variables into the runtime of your program. And these variables can lead to branching states. And now, instead of an execution trace, which is usually just a list in case of classical debugging, you now get an execution tree, which is a branching tree. And you get constraints assigned to all the nodes in your tree. And that's even harder to visualize. But we actually found that the debugger could, like the user interface could just be reused. So we needed to make some tweaks to Visual Studio Code or in our extension to actually map out the symbolic execution tree. But yeah, that's where we're coming from. So first of all, we wanted to have a debugger just to save us time and give us more confidence in our manual code reviews. And then also we wanted to have a tool that makes our formal verification more efficient by mapping low-level EVM states back to the Solidity source code. So these were our initial motivations to invent Symbolic. And yeah, I agree to everything that Nick said, like all the problems that he had while developing Truffle, we are seeing the same. We are facing the same problems right now, and we are very happy that Nick took the effort at the Ethereum Foundation and is now building this ETH debug format, which will save us a lot of time when we try to decode Solidity variables from low-level data structures, especially when it comes to optimized code.
All right, what I'm hearing is you guys started Symbolic because you needed something better than what you were having at the moment. And I'm pretty sure that's also how the Wake framework started, because Aki was using, I believe it was Slither, but then they were like, we need something more powerful. And after Wake framework was built, Aki released a VS Code extension called Tools for Solidity. Stefan, maybe you can talk a bit about the extension, what it is, and what's coming up for it.
Yeah, hey everyone. It's my pleasure to be here. My name is Stepan, and I'm a team lead and ethical hacker at Aki Blockchain Security. And previously, I was a mobile apps developer for 10 years in legacy banking and centralized finance. I started developing mobile apps when it was Android 2. And yeah, it was kind of pain. And you know why? because the development tools were horrible. There were a terrible IDE named Eclipse, Java 5, designing UI in cutting-edge XML, and the device emulator was laggy and literally unusable for debugging. So a lot of my Android colleagues switched to iOS development because of that lack of quality tooling. And yeah, but year after year, Google is improving the development tools and a lot. Today it's a totally different world. Android Studio IDE is based on JetBrains IntelliJ IDEA, which is top notch. And today you are coding in a beautiful Kotlin language, including UI. Emulators are butter smooth, and debugger is complex and fine-tuned. And why I'm talking about that? Because I see a lot of similarities in development for Ethereum. I think we are still early, but there is no such a Google in Ethereum world to fund and build the tools. There is only the community and small companies. So we are the ones to build the tools here. Yeah, so for quick prototyping and testing, we have Remix IDE with nice UI for deploying and interacting with contracts. For more serious development, we have VS Code with a bunch of available extensions focused to Solidity development, and frameworks like Foundry, Hardhat, Truffle, or Wake. But as I said, we are still early, and I'm really looking forward to see more nice development tools to come in the future, because I think it's very important for developers' adoption. And yeah, before I will continue on our tools for Solidity VS Code extension, does anyone want to add anything to this topic?
Yeah, I think we know from the Solidity developer survey that I think more than 2/3 of all Solidity developers, at least from those who filled out the survey, are using VS Code. So that's also why at runtime verification we focus our efforts on making Symbolic available for Visual Studio Code, because that's just where the users are. And we don't want it to develop a custom user interface, well, for two reasons. The first one is obviously building a custom user interface for a debugger is a non-trivial task that takes a lot of time. And the second one is, well, who will actually use it if all the users are using Visual Studio Code? So we didn't want to take developers out of their IDE of choice for debugger. So that's why we opted into Visual Studio Code.
Yeah, exactly. As we with tools for Solidity. So I will shortly talk about our extension, which is using Wake internally through the LSP protocol, and it's like a front end for the Wake. And aside from usual features for development, like go to definition, find all references, code lengths, etc., we have also some special ones, like generating inheritance graph or control flow graph. There is also visual test coverage feature, so you can see covered lines directly in the code, even real time during the fuzzing. But most importantly, our detections UI, so you can see vulnerability detections from the static analysis directly in the VS Code in a nice tree view where you can filter them by impact and confidence and group them by these criteria or by file or by detector. And when you click on the issues, it navigates you to it into the code, and these potential vulnerabilities are also highlighted in the code, so it's very useful during auditing and even during the development. And finally, last few months, Lucas was working hard on our next killer feature, which we announced recently on ETH Prague, and will be released soon. So I'm passing the word to Lucas, and he will tell you more about our project Sake. Thank you.
All right. Thanks for the word, Stepan. Currently, as Stepan already said, we have an LSP server. We provide static analysis and testing tools, etc. However, there is still a lot more to be done for a better VS Code Solidity developer experience. A nice example here is the Remix IDE, which offers an intuitive UI for quick prototyping and testing on a local chain, which is something we are still missing inside VS Code, and especially for which there really aren't many alternatives, especially within VS Code. This forces developers to use different IDEs, which can really disrupt the workflow. We recognized this gap and decided to expand tools for Solidity with what we internally call Sake, and it's the next major addition to the extension tools for Solidity. Sake is a Remix-like UI, which enables users to quickly test their contracts and see the results immediately inside VS Code without the need to switch any windows. Firstly, compared to Remix, Sake simplifies the compilation process. It automatically detects all the contracts within your workspace and compiles them all in bulk, which saves developers both time and effort. Additionally, Sake also selects the correct compiler version, so you don't really have to worry about the Sol-C version either. After compilation, you will be able to deploy these contracts on a local chain, Anvil, from specific accounts. You will see the deployed contracts along with their addresses, balances, and other relevant details. Sake also generates an interface for the contract API, complete with callable functions and input fields. This allows you to make contract calls and view the results and call traces directly in the sidebar and the output window inside your own VS Code. Sake is currently undergoing beta testing within our own team, but we aim to release it publicly as a part of tools for Solidity, so all the current users can expect these features to be available to them soon without any additional setup. Yeah, that's all from my side. Thanks, guys.
All right, so we have Symbolic, we have tools for Solidity. Nick, what's your view on VS Code extensions?
They're essential. VS Code is the most widely used integrated development environment today. So, I don't think we could really grow our skills as a developer community until we have good tools that run locally in your development environment like VS Code. And since VS Code is extremely popular, and like with debugging, they have excellent infrastructure for supporting debuggers of like any language. And so to me, it's a no-brainer. You, of course, give the developers the tools that they need to make their life easy. Now, I mean, for a slightly more nuanced take, my hope is that we could separate concerns here. I'm a big fan of the approach that I sought to maintain while working on Truffle and Truffle Debugger, in that Truffle Debugger was a standalone library for doing debugging. And then the VS Code extension that we built was just an interface to that library. And this, so we had a Truffle Debugger was a standalone software component, and then we had a separate software component for integrating VS Code's what they call the debug adapter protocol. And this meant we could offer our debugger with multiple interfaces. And by Truffle's end, we had a CLI, we had a VS Code extension, and we had a web app that all offered approximately the same debugging experience without having to reinvent the core debugging logic each time. And I think this is the right approach, especially if VS Code should fall out of vogue. You don't want to have to rewrite your debugger completely. Maybe separate concerns up front and save yourself the trouble.
Yeah, absolutely agree to this point. So, Visual Studio Code right now is the most widely used IDE, but for sure, it will not be the most popular IDE forever. There will be, I don't know, maybe in 2 years, maybe in 3 years, maybe in 5 years, maybe next month, there will be a new hot IDE. And we don't want, we don't want to lock ourselves into this, into Visual Studio Code. So Symbolic, our debugger, is also built on top of the it's built on top of open standards wherever we can. So it's built on top of the debug adapter protocol, same as Truffle, on the one hand. Then on the other hand, it's built on the JSON RPC protocol and the standard JSON format that the Solidity compiler generates, and then hopefully the East debug format that Nick is currently working on. So yeah, we try to build on open standards wherever we can so that we don't lock ourselves into. And Visual Studio Code actually makes the separation of concerns very easy to do. So I think the debug adapter format was actually invented at Microsoft, at the Visual Studio Code team. So that's pretty nice.
Yeah, it's really nice. That's the right approach, right? Like, Raul, if you're trying to build a good tool, don't hurt yourself in the process by locking yourself into someone else's like non-standard, software library or software tool or whatever.
Yeah, 100%.
Yeah, I really liked you guys' comments and also Stefan's analogy of how the whole testing space from Google Android has evolved over the years. And Ethereum, is over 10 years old now. So we have the most available tooling right now, since ever before. But next, I want to take the conversation to fuzzing and formal verification. Joseph, could you maybe highlight some types of fuzzing and walk us through?
Yeah, thanks. Maybe first, we should define what is fuzzing. And I believe Michael from our team is the best guy to describe that.
Yeah, sure. I can start with that. So fuzzing is like a special technique of testing. In general, we are speaking about smart contracts now. So it's a special technique of testing smart contracts. And it's all about generating random data. So we generate random data as inputs to contracts, and we pass those data as parameters to functions. We also can, let's say, randomize the sequences of operations that are performed on the contracts. So we basically generate random transactions, like the order of transactions and types, like what functions we are calling. And then we generate random data. And this way we can test multiple different scenarios that would be very hard and, let's say, labor intensive to test with like unit testing. And when it comes to auditing, because we are smart contract auditors, it's also easier for us to prepare one single fuzz test that basically tests all the possible test cases instead of defining or implementing unit tests for each function and each test scenario. So it turns out it's easier to prepare more complex fuzz tests that can be easily maintained, at least for us, than like preparing all the unit tests and testing different scenarios. And yeah, so I think there are many different types of fuzzing or maybe kinds, and they are not very strictly defined, and everyone tries to come up with something new. But we are like internally at Eki thinking of fuzzers is like there's some black box fuzzing, let's say. So the fuzzer basically does not know anything about the code. It just receives probably some like input, for example, the coverage. So the fuzzer knows that it increased the coverage with some transaction, so it keeps up the transaction because it probably helped with like covering more code, and this way, with additionally with mutation, like mutation of the data, it can probably cover more of the code. But this we call it black box fuzzing because the fuzzer doesn't know what it's doing actually. But Wake takes different approach. We call it guided fuzzing. So basically, we as testers, we define everything we want the fuzzer to do. So we are responsible for defining the transactions. What if we want to run a single transaction, or maybe let's say that a function needs to work with tokens. So obviously, we need to mint the tokens or somehow get the tokens and then make the approval. Without the approval, the next transaction wouldn't make sense. And we are responsible for defining these steps, as well as the random parameters like the data. A good example here can be, let's say we are working with an enum, and it doesn't make sense to define or like generate a random value up to 256 because we know the enum value may be only let's say to 4. So we also generate the random data and we define how random the data we want to be. We can specify like the probability of generating the edge case values. So we can define that, let's say in 10% of the cases, we want to generate the minimum value, the maximum value, and the 0. And this way we can tune the parameters that are passed to the contracts. What we also do quite often, especially in audits, is that we basically redefine or re-implement the protocol we are testing, but in Python. So we have basically two implementations, the original one in contracts and a different one in Python. Usually the one in Python is written by a different person because we are auditing and the project already exists. And this way we can basically do differential testing. We can differential test the original protocol and the implementation in Python. It's simpler to write the same logic in Python because it's not that restrictive and it doesn't care about types. So yeah, it's easier and we can compare like the observations from the contracts and from the implemented Python model and see if there are some differences. And quite often there are some differences, especially when it comes to some math, like complex math, or even like access controls because of different random order of operations. So yeah, I think that in general, testing something in a different language than the code we are testing gives us an opportunity to do differential testing. And also quite often the projects rely on, let's say, external projects like or components, for example, Chainlink, Aave, or something else. And yeah, sometimes it can cause problems to fuzzing, but we are trying to solve these cases with fork testing. So we run like a full node locally, then we fork the full node with all the external dependencies already deployed with like in a reasonable state. And this way we can basically deploy all the contracts that we want to test, and the dependencies are already deployed and we don't need to set them up. And yeah, it's easier for us so that we can only focus on the contracts that we want to fast.
Yeah, maybe I'll add to that, like fuzzing is a technique and it depends on the tester how to implement this technique. And the approach of, I would say, like, for example, Echidna is the thing that we call the black box fuzzing, which means the fuzzer itself has to like develop the way through the whole space of possible variants, how to interact with the contract. But in our case with Wake, we are trying to guide the fuzzer. which means the developer or the tester has to write the fuzz test, which means like the instructions for the fuzzer, where should it fuzz, which function should it fuzz, which like the instructions or which should be the input values for the each function. And this kind of like allows us to have a very specific fuzz test written, and it in the end allows us to have a fuzz test that is running in a time period that's finite. Because with the black box fuzz testing, what happens is that the fuzzer runs for infinite time period and doesn't discover anything. In our approach, the tester basically instructs the fuzzer how to find the possible vulnerabilities, and it narrows the space, which means it will bring the results like much sooner or with much better probability.
Yeah, exactly. Like we are in full control of what the fuzzer does, and we can even check the testing coverage that we are really covering some branches that we intended to. So I think this is the greatest advantage compared to black box fuzzing, is that we have the full control of what the fuzzer does. And if it doesn't do what we want to, we can just change the parameters or the code, and it should do whatever we want to.
Of course, like the drawback is like the tester has actually to write the code, which in the case of the black box fuzzing is not there, because like the black box fuzzer just runs. But in this case, like it's a more hands-on approach that actually like the tester has to write instructions for the fuzzer where the fuzzer should go.
Yeah, and that's basically why we've chosen Python, because it's very easy to write the code in Python, and like even the debugger is very powerful. We don't need to recompile the listing files again and again. So I think Python is the perfect choice for that.
Awesome. So that was about fuzzing. Raul, maybe could you explain what is formal verification?
I can try. So there's a famous quote from a computer scientist and mathematician who was called Edgar Dijkstra. He was a Dutch computer scientist, and he's famous for the quote, "Program testing can be used to show the presence of bugs, but never to show their absence." And I would argue that formal verification is the closest that we can get to in terms of proving the absence of bugs. Well, it's not quite the case. We can never give you a 100% guarantee that your code is 100% bug-free, because that would lead us into philosophical discussions of what constitutes a bug. But what formal verification can do is it can prove that your smart contract system or your software system in general adheres to a formal specification. So, and that is really a very strong correctness guarantees. It's not just, hey, yeah, it really gives you a mathematical proof that your program adheres to its specification. Now, when I say specification, well, then usually I lose a lot of my audience. But I think a good way of thinking of specifications is thinking of test suites. Test suites are, in general, they are written in a formal language. They are understandable by a computer. They are executable. So, in essence, they are formal. They constitute a formal specification of your system. And formal verification can now be used to execute your tests and prove that your tests do not fail under any circumstances. So that's a difference from fuzzing. Well, fuzzing can point you to a counterexample and can say, hey, this test case fails with these concrete inputs. But a fuzzer can never tell you, well, I'm 100% sure that the test case cannot fail under no circumstances. That's something that only formal verification can offer you. So that's one way of thinking about formal verification is it's just testing, but instead of testing some random inputs or some fixed inputs, it tests all the possible inputs of your smart contract. Notice I'm not saying you shouldn't be fuzzing, quite the opposite. Fuzzing and formal verification go very much hand in hand, and you should be doing both. You should use fuzzing heavily and catch all the low-hanging fruits, basically. And once your fuzzer is happy and is giving you green check marks, then you shouldn't stop there. You should actually try to go one step further and try to use a formal verification tool. The formal verification tools that we have for Solidity and EVM today do a very good job in reusing your test suites that you have written in Foundry, for example, and taking the same input format and using them as a specification for your formal verification tool. So that's the way I like to introduce formal verification. Is think of it as testing and getting 100% coverage over all your possible inputs.
Yeah, I think that. Oh, sorry.
Oh, go ahead, Michal.
I think that there's also a difference in like the execution time because based on our experience with fuzzing, it's enough to run the fastest for even a few hours, and this way we get most of the bugs we would ever discover. So we spend some time, of course, on writing the tests that we are using Python, but when it comes to running those tests, it's enough to run it just for a few hours to get the result, which is, yeah, I think it's very comfortable for the users.
Yeah, no objection there. Fuzzing is definitely the faster technique. It's faster than formal verification. Formal verification is pretty compute intensive. That's why I mean you should be doing both. Fuzz it heavily, harvest all the low-hanging fruits, and then use a formal verification tool to hammer out really all the edge cases. Because in the end, well, sometimes a formal verification proof can take you some hours. In some cases, it can even take like 24 hours. But at the end, if you have that time to wait another day before you deploy your smart contracts to the mainnet, and you have another day, you can wait another day and let the prover run and actually give you a proof or a counterexample that your test case cannot fail anymore. Then it becomes a no-brainer. Of course, it's not just compute power, but formal verification is also like less automated than testing. So in most cases, you will need to put in some additional work to make your proofs pass.
Yeah, absolutely. I also wonder how good or maybe bad does formal verification scale with the size of the project? Because for us, it means that we need to write more test code. It's quite obvious, but we still basically can fuzz any project, even like with thousands of lines of code, or with some, let's say, special requirements. For example, if the project is a cross-chain project, so it interacts, or basically the solution is a cross-chain solution. So there are some contracts on chain A, some contracts on chain B, and basically with fuzzing we can do anything. So we can even like simulate the communication from chain A to chain B. So I think there are no limitations for fuzzing because we can basically emulate anything.
Yeah, I can only speak of one-time verification tools here, but we used our tools like KVM, Control, on like real-world code bases that are highly non-trivial. Just to give some example, we used it to formally verify parts of optimism parts of Uniswap, Blockswap, Laxo, Lido. So these are not just simple ERC20 contracts, but these are huge smart contract systems. And we were able to successfully prove critical properties about these protocols. So one very nice feature about symbolic execution is, for example, that it does not, the complexity does not grow with your state complexity. Like if you have lots of state variables in your smart contract, usually in symbolic execution, you just replace all your storage variables with just one symbolic expression, and that actually makes huge code bases much more tractable. Another thing that we can do in informal verification is what we call over-approximation. So we have a critical property, and instead of showing that the critical property holds on your exact smart contract system, we can show that the property holds on a larger class of smart contract systems, so not just for your smart contract system under the hood. And that makes it sometimes easier to reason about smart contracts by generalizing them, which is a little bit counterintuitive. But the cool thing here is when you do it in this way, then your analysis is sound. That means once you have the proof for a more general smart contract, then it will certainly also hold for the smart contract that you actually want to analyze. Now, that's something that we don't do too often, but it's one technique that that can be used to make formal verification more tractable. But yeah, in general, we at least at runtime verification, we haven't hit the wall yet in terms of complexity. And if you remember my statement from the beginning, our techniques were researched at NASA, and the code that they're writing at NASA is like orders of magnitudes more complex than what we see in smart contracts. And it is useful there. So, and when our smart contracts are not 1 million lines of code, then formal verification, I think, is a tractable technique. And if we have smart contracts that exceeds 1 million lines of codes, I think then we have a different problem.
I have just one last question, and I'm just going to ask it in 2 rounds. So how exactly does fuzzing and formal verification complement each other? I was going to ask Nick, but I think he has some issues with becoming a speaker at the moment. So if anyone wants to take it, feel free. If no one wants to take it, I'm going to assign Michal. How does fuzzing and formal verification complement each other?
Yeah, I think that, as Raul said, it makes sense to use both of the techniques because fuzzing cannot prove you that something will hold under all circumstances. So it definitely makes sense to use like formal verification if it's possible. At the same time, it quite makes sense to do fuzzing because it's quite simple. We even tried to generate like fastest using GPT. So and we got some quite good results if of course the tester can modify or adjust the code to make sense. So yeah, I think it's quite easy to write fastest, and it's something that can be reused. So if the project just updates the code, it's often very easy to adjust the fastest, and it can give exact numbers that show how it fails, or it does not even like prove there's a no bug, but it can be used for analysis. For example, even for tokenomics, so we can analyze how the project behaves in time, and we can analyze the code coverage. So basically, we can even make sure that we are visiting all the possible branches that we wanted to visit, and given some values that lead to these branches. So you also control what branches, or like, yeah, basically execution branches we are visiting. So yeah, I think it makes quite sense to use both of these techniques.
Nick or Raul, do you guys have anything else to add?
Yeah, can you hear me all right? Sorry for the technical difficulties.
Yeah, we can hear you.
Great. I just keep switching back between phone and computer. So, like, I see them complementing each other because, like, formal verification is extremely powerful, but it requires you to understand how your application should work, which I don't think is easily solved, right? Like, certainly not understanding how your code actually behaves, but even understanding the requirements you intended, I think requires a lot of, soul searching at least. And so using fuzzing, like fuzz testing, you generate arbitrary examples, and that can help inform what your requirements are. Maybe you missed something, right? And then you see there's a case that failed or a case that behaved in a weird way. You can then use that to help guide your specification and define the properties that you want to hold. And I mean, I just think you're not checking all the boxes of best practices if you're trying to build a financial application that can handle hundreds of millions of dollars. It's like writing software for NASA. It's the domain, like the requirements of our domain are just as challenging as, building a rocket ship. I mean, maybe, it's a different goal, of course, but if you're building large financial applications, you have to get them right. So use every technique is, I think, a very important practice.
Yeah, I also think that fuzzing can really help in case of DeFi. Let's say that we are working with some DeFi protocol, and there may be rounding issues, or maybe just hidden bugs that cause that the numbers are not as exact as we want them to be. And using fuzzing, we can track basically like number errors and evaluate if the errors are small enough. So basically, we don't need to care, because rounding basically can happen, and we cannot do anything about that. Or these errors may grow over time and cause some troubles to the protocol. So I think that fuzzing can help even in this case.
Yeah, I really like the point that Nick made. Formal verification requires you to have a solid understanding of the requirements of your code base, and I think that's where fuzzing is really a stepping stone towards formal verification. As I said earlier, when you task a developer to write a formal specification of your software system, most of the time he will just be lost. If you ask him to develop a test suite or a fuzzing test suite, then he knows exactly what to do. And a test suite is nothing else but a formal specification. It's machine readable. It makes assertions about your code. So that's a perfect formal specification. And I think that's where formal methods can learn a lot from testing tools, from like classical fuzzing and testing tools.
All right, thank you everyone for joining. We are over the hour, but if you have a couple more minutes, maybe we could see if anyone from the audience has any questions. If not, we will be closing the spaces shortly. Or if someone else from any of the speakers want to say some closing remarks.
Well, I just wanted to thank you all for inviting me to speak here today. It's been a great discussion. I really enjoyed being a part of it.
Thanks for joining, Nick. All right, it seems like we have no questions. So with that, I want to thank all of the speakers for joining us and talking about securing the crypto space. Thank you, everyone.
Thank you, everyone.
Thanks for joining. Take care.
Thank you.
Thank you very much. See you.
Bye all.
Thank you, guys.